Hello students, we are going to review practical 14. As I mentioned during tutorials, we're going to do it in a slightly different format, partly due to time constraint and also partly to give you a little bit of time to think through some of the experiments which you have done, and then think about what are the potential mistakes that you could have made. Okay, so allows you to maybe be a little bit more reflective, and when you are approaching say practical 16 or future practicals or whatsoever nearing your exams, I think it will help. Okay, yeah, so without further ado, we'll begin the review. So first, we look at the first question. Okay, so for the first question, you are provided with FA1. If you remember, FA1 is a very nice green. Okay, so it contains two cations and two anions. Usually the clue given to you will be listed here. So two cations, two anions, and then they are listed in the QA notes. Okay, so just go straight to the QA notes if you need any details later on to help you in your observation. Okay, and then remember very specific instructions over here. At each stage of the test, you are to record details of the following: color changes, formation of PPT, and then solubility of the precipitates in excess of the reagents. Okay, so when gases are released, you're supposed to identify them, and if they are being described in the passage, you're supposed to carry them out. Okay, so you should not be carrying out any additional tests. So these are the standard instructions given to you in your practical exams. Okay, so over here we try to give you a taste of what you're going to expect in a real exam. Okay, so right, so we have a without further ado, let's jump straight into the video review. Okay, so where I'll be demonstrating the series of experiments in 1A and B.
Okay, we are going to look at practical 14 experiment A, where we're going to add 2 cm depth of FA1 into the test tube. So we'll try to do that first. So this is FA1, 2 cm depth. Just going to introduce to this particular test tube. Okay, so this is the test tube containing the solution. Okay, then the next thing we're going to do is we're supposed to add in sodium carbonate. So this is sodium carbonate. But before we add in, we need to ask ourselves the purpose of adding sodium carbonate is probably to precipitate out insoluble carbonates. And at the same time, if the solution is acidic, you are expecting CO2 to be evolved. So if CO2 is evolved, then what do we need to do next? We need to test it with lime water. Okay, so in that case, we need to prepare a separate test tube and add some lime water in. But again, how much lime water to add is always a question students have in mind. Yeah, but we need to consider several factors or several things. So the first thing we need to ask ourselves is, are we adding a strong acid to a carbonate where a lot of CO2 is going to be involved, and then a lot of bubbling, and then we expect gelatinous, a big amount, huge amount of white PD to evolve. Yeah, or are we adding a weak acid in this case? Yeah, so and then of course the next question to ask ourselves is, what does FA1 contain? FA1 contains 2 cations and 2 anions. So the acidity, if any, is likely due to the salt hydrolysis or the hydrolysis of the cations having high charge density. Or if not, it could be ammonium. Ammonium will also hydrolyze partially to give you H+. And the concentration is not likely to be very high. So the amount of H+, not a lot of CO2. If we have too much lime water, then we might miss the white PPT formation. Okay, so with all this factor in mind, then we know that we probably shouldn't be adding too much lime water. Okay, so with that, then we just add in the lime water, just enough to fill the bottom, and then we need a delivery tube. So our delivery tube is over here. Okay, we need to prepare everything first, and then after that, carbonates, get it ready. We don't dump it in first. Okay, we put it at the sides. Okay, so it's always a good habit to put it at the sides, and then after you just tilt some in. Yeah, so that you'll be able to get enough CO2. Okay, yeah. So this is a very good technique which I hope you all can learn. So just put some carbonate at the sides. Okay, then get everything ready. Okay, so once you are ready, I mean in the exam, just put it in and then plug, and then you swirl. Okay, so make sure you plug it in properly, because if not, the CO2 given out will not be able to give you the PPT you want. Okay. Okay. What did we observe now? Can you take a look? Maybe is it very obvious that you are getting a cloudy, milky solution containing white PPT? Yes. Okay. Okay. So I think we can stop here. Okay. Then right now, I'm just going to take it out. We'll observe a little bit. What do we really see? Can we see that there are some things sticking at the sides? Yeah, but we can't really tell. So that's not something you want to observe, because these are the sodium carbonate which we did not manage to mix well. So in exam, if you want to, you can just tilt them a little bit and just make sure that you try to mix everything well. Okay, or you can use a glass rod to force them in. If not, I think it's okay. Yeah, so you can just swirl until they are well mixed. Okay, so this is a good technique that you probably want to learn. So one way is you swirl hard, and then another way is like this. Okay, yeah, so this is the final appearance of the solution, which you should observe it in your lab worksheets. So this is probably written as the green PPT, and then just now you observe effervescence. So effervescence, remember, is the word which you should use for gases like CO2, oxygen, and hydrogens. Yeah, so in this case, effervescence of colorless, odorless gas, because you don't smell anything, and then gives off a white PPT in lime water. So that's what you should be observing. Okay, so I hope this is clear enough. Then next, I'm just going to put this at the side first. Okay, so we're going to move on to part B. Yeah, so part B is a little bit more challenging. Okay, so I'm going to close this off because we don't need this anymore. Okay, so for part B, you're supposed to use a boiling tube. So we have a boiling tube over here. So this is a boiling tube. You can see that it's much thicker. Okay, you can place a larger volume of solution in, and then you are supposed to use a measuring cylinder, and then put in 6 cubic centimeters of aqueous ammonia. So I'm going to take a measuring cylinder. Okay, so this measuring cylinder over here. So I'm going to put in 6 cubic centimeters of aqueous ammonia. Okay, because later on you're supposed to add aqueous ammonia in dropwise. Okay, I'm going to put in 6 cubic centimeters of aqueous ammonia. Basically, I'm just following instructions because this is what you're required to do in lab work anyway. Okay, so follow instructions, 6 cubic centimeters of aqueous ammonia. Okay, and then so I need to place 2 cm depth. Okay, so in this boiling tube, I'm going to put in 2 cm depth of Fa1. Okay, so 2 cm depth. Yeah, because the boiling tube has a much wider base, so 2 cm depth will be quite a bit. So I need to introduce more. Okay, and of course a little bit more. So this is probably about 1.5. Okay, so that should be sufficient. Okay, so this is 2 cm depth. Okay, so what I'm going to do now is I'm going to add in 1 cubic centimeters of aqueous ammonia using a dropping pipette, and then I mix the content. Okay, so I'm going to, I think I explained the tutorials before, maybe during lab practice. So I'm going to do something called layering. Okay, so what exactly is layering? Okay, so what I'm going to do now is I'm just going to add in ammonia dropwise. Not exactly 1 cubic centimeters, but I'm going to add in dropwise. Okay, I just want to let you observe, because this is a good technique which you can use on your own. Okay, so first of all, right, I add in 1 drop. You need to observe. Okay, can you see that the surface, okay, is a little bit of green precipitate, okay, without me swirling it. Okay, I'm not sure if it's clear on the camera, okay. Okay, but when I swirl it, it dissolves, or you can still see some hanging around. Okay, the reason why we do layering is to give us an idea what might be the identity. But of course, this green PPT is a bit, misleading because we may be thinking that it's iron 2, but it's actually not iron 2. Okay, so we're going to add a bit more. Okay, maybe half a bit, just for you to observe. Okay, I'm not adding everything. Can you see some, the top layer? Okay, can you see a deep blue solution? Yeah. Okay, and then followed by some at the side along the walls over here, along the walls. Okay, a bit of reddish brown PPT at the side. Yeah. Okay, why is this called layering? Because I'm not swirling, I'm adding in, and then at the same time, I'm observing how the solutions slowly settles down. Can you see that? Okay, now can you see that the PPT inside the solution below the dark blue ring is actually a little bit more reddish brown? Okay, so I'm going to add in everything, okay, without swirling for you to observe. Okay, right. Okay, can you see over here? Okay, so there's a rim of dark blue solution. So it does give you a clue already. Confirm it contains copper too, right? Because if not, you wouldn't get the dark blue complex. The reddish brown thing floating around, I don't know what they are, probably some iron. Okay, but you shouldn't be recording this. Yeah, you shouldn't be recording this. This is for you, for your own checkpoint, like for you to check what it is likely to be. What you should be recording is you swirl this solution. Okay, remember two kinds of swirl. One is the very hard one, the other one is like okay. You should be recording this. Okay, you should be recording this. Okay, so at this instance, because if you look at your worksheet, what did they ask you to record? After you add 1 cubic centimeters, what is this? You should be saying brown, right? Am I right to say this is brown? I mean, you're not lying to yourself. Of course, you know that they are copper too, but it's not copper too. I mean, you can't tell it's copper too from here, but just now, without swirling, it gives the game away. So that's a key thing. So this is a good technique, which I think all of you should learn. And then after that, they ask you to repeat until it's empty. So we'll try to do that. We'll keep doing that. So 1 cubic centimeters, bits and pieces of it. Okay. So I'm going to hold this equals ammonia. Okay. I'm going to add in drop by drop slowly. I want you to see the difference. Okay, can you see the blue PPT appearing? Okay, I'll try to add to the side, clean the side a little bit. Okay, so can you see that it's giving the game already? Okay, I'm just going to do this. Can you see that there's some dark blue solution flowing at the side? Can you see that? Without me swirling very hard. Okay. Okay, right. So I'm going to swirl a little bit. Can you see some green PPT forming? Actually, they're not green. It's actually a mixture. Okay, so now it's very clear already. The solution is now a mixture of PPT. It's probably a mixture of blue and reddish brown, if you want to call it. Okay. So right now, I'm just going to swirl. And then I try to observe this color. So again, it goes from like brown to now mask with a little bit of blue. I don't know whether you observe that. Okay, so the next the next bit is important. Okay, so again, I'm going to tilt a little bit so that you can see. Can you see the side, the dark blue forming from the side, the walls? Okay, right. Okay, I'll wait for it to settle a little bit. Now, I'm just going to turn a little bit. I want you to observe this portion. Can you see that it's a little bit like reddish brown bits over here? Yeah, so I'm going to tilt a little bit. I'm just going to swirl even more. Okay, going to swirl and then to ensure that it's well mixed. Yeah. So after you swirl, you realize that it's a bit green, blue, etc. Right? Yeah. Okay. So I think that's almost about it. I'm going to just add in everything because any more delay, you wouldn't be able to observe very interesting thing as well. Yeah. So after I added in everything, what do you notice? The solution now becomes, it's like a mess, like a dark blue mixture kind of mess. Okay. So I can turn the side as well. Then you can see the walls of the container, right? It's a bit, if I used it, it's a bit reddish brown. Can you tell? It's a bit reddish brown. Yeah, so it's not like, it's like some of the reddish brown PPT gets stuck. So probably reddish brown PPT, dark blue solution. I don't know. With some green, you can't really tell. Okay, sometimes to play safe, I think it might help a little bit if I add in a little bit more ammonia. Okay, because I wouldn't know earlier on, right, whether I've added in too much effluent. Yeah, so sometimes to play it safe a little bit, I'll add in a little bit more ammonia. Okay, so this is the final solution, the color which you should be recording. You can't really tell, but you know that you have a bit of blue PPT, you have a bit of brown PPT, and then now the solution is dark blue, so it's probably a dark blue mixture. If you follow the instruction next, right, they ask you to filter the mixture. Okay, so filter the mixture to where? So probably filter to another boiling tube, probably. So we'll try to do the filtering. I'll filter funnel. Fold the filter paper. Okay, I just want you to take note of the color. Okay, I don't know what is really the best way, but so I just pour it in directly first. Okay, I really want you to observe. Okay, if I can tilt the thing a little bit, okay, I'm scared that it will just flow out. Okay, so now you can see that it's really a dark blue solution as the filtrate. Okay, of course, in real exams, you don't hold it like that. I mean, in real exam, you're just going to leave it here, right? But for now, I'm doing a demonstration, so I'm holding it. It's ready for you to see, and then I just want to show you a little bit. I hope I can tilt a little bit here. Okay, I don't dare to tilt too much. Okay, you can see a little bit of brown PPT at the side, right? Yeah. Okay, so when I was marking the practical, right, quite a lot of you mentioned that it is green PPT turns brown. Green PPT, which means you are thinking that it's iron 2, it wouldn't turn brown so quickly. Definitely wouldn't turn brown so quickly. Yeah, it will take a bit of time, maybe half an hour or an hour. And even if it turns brown, right, it will be the rim at the side of the residue most exposed to the air, and that will turn brown. Yeah, so in our case here, okay, so I think we are filtering for quite a while already. I can just tilt a little bit more, so I give myself a little bit of courage to tilt it. Okay, you can see that it's really, really very brown. Okay, I don't know if the camera is clear enough, but yeah, it's really quite brown. Okay. Okay, so we're going to hang on for a little while. And yeah, so later I'm going to transfer 2 cm depth of the filtrate to a test tube. Okay, so instead of me transferring to a test tube, I'm just going to have a test tube over here. Okay, so just going to get the filtrate directly. Okay, like this. Okay, and then, yeah, so this is a good habit. just to showcase to you. Because many a times I noticed that, students during practical, you just sit there and wait. Sometimes you can just play around with test tubes. Like, for example, now I have this test tube, right? Yeah, so after I filter some of the solution in, then I just transfer it into this. And then later on, I know that I need about 2 cm depth of the filtrate to add sulfuric acid. So later on, very quickly, I will transfer this back into the boiling tube. And then after that, I'm supposed to wash the residue thoroughly with deionized water and then discard the washing, retain the residue for use in part C. Yeah, so I think as a student doing practical, you have to be a little bit strategic in the way you work on the experiments. So where possible, you can always move ahead and look at what is likely to happen next and what you're likely to do. Yeah, so these are all very important skills which you should pick up along the way. Okay, so I think I should have enough already. I'm not sure. Okay, so I'm going to tilt it. I'm going to really, really try to tilt it without fearing that you will. Can you see that it's really, really reddish brown over here? Yeah. Okay. Yeah. So I'm going to just shift this over. Okay. And then for this filtrate, right, I'm going to add in sulfuric acid. Okay, now this portion, right, this part, right, a lot of students don't get the correct results. So I'm going to take sulfuric acid first. Okay, so this sulfuric acid. Okay, so I'm going to add it in. And then I want you to observe. Okay, so over here, right, I'm going to add in. Okay, so please observe. Very, very slowly. Don't add too fast, so drop by drop. Okay, sure. Again, I'm going to do layering. Can you see that PPT starts to appear? You will miss it if you add very fast. Can you see? The PPT starts to appear at the bottom, right? Yeah, because usually the solution will sink to the bottom. Okay, so just for you to take note of it. Okay, of course, if I swirl, right, the solution will be like a pale blue PPT swimming around dark blue filtrate, something like that. Okay, so I'm going to add in slowly, drop by drop. You can see the pale blue PPT starts to appear. So your hands has to be a little bit steady. Okay, can you see the pale blue PPT forming already? Yeah, so any more addition will cause the reaction between the copper 2 hydroxide, okay, with acid. And then after that, you'll be an acid-base neutralization reaction between copper 2 hydroxide and sulfuric acid, and then now you get a pale blue solution. Okay, yeah. So for quite a number of you, right, because you add in very fast, you don't get to see this part. Okay, so maybe I can try to showcase to you a little bit. Let me take a little bit more of this. I'm going to give you a negative example. Okay. So I'm going to give you a little bit of negative examples so that you don't commit it. You don't commit this mistake again. Okay. So what a lot of you did was this. Okay. What you did was you straight away spam it like this. Let me show you what negative example. Okay. Shouldn't be doing this. Yeah, you don't see anything, right? It's like magic show. Straight away, the spiraling dark blue solution just spiral off and then give you a solution. That's what you observe. You don't see the pale blue precipitate. So always remember add dropwise. Okay, so that is the part. I hope you can remember for it goes. Okay, and then now the next part is I'm supposed to wash the residue thoroughly with deionized water. Okay, so now you can see that the residue is very, very clear already. Not clear, but it's reddish brown. Okay, so I'm going to, what do we really mean by washing with deionized water, right? It's really taking deionized water from here, and then I just wash it one round. Okay, just take a look, just washing it one round to make sure that they are clean. Okay, yep.
Okay, right. So now you have seen the experiments from 1A and B. Okay, so we'll look at one of your classmates' response and then discuss accordingly. So if you remember from 1A, right? Uh, so the solution we added some sodium carbonate. So remember some of the precaution which I told you about. So you are expected to observe some green precipitate. Okay, so some green precipitate. If you recall what you viewed earlier on, you have observed it. And then, as I mentioned, the addition of carbonate is an indication that you should be observing either the precipitation of an insoluble carbonate or maybe potential acidic solution. Yeah, so if you observe effervescence, which is a keyword you need to use here. So effervescence is a keyword. You need to write it down and you need to test the effervescence. So in this case, you need to test for carbon dioxide. So you need to bubble it into lime water. And as I mentioned earlier on in the lab, when you bubble into lime water, make sure you don't use too much lime water because you don't know how much H plus is present. So the amount of CO2 may be too little. If it's too little when you bubble in, you can't really observe. Okay, try not to test CO2 using litmus because it's not conclusive. SO2, NO2, these two are acidic gases which will also turn moist blue litmus red. So don't test CO2 using litmus. Okay, test CO2 by bubbling it into lime water. Yeah, okay. And I think I went through quite extensively with regards to 1B. I taught you guys the layering techniques, but you should not be writing down every single observation when you do layering. So you have to be a little bit careful here. Okay, so if you kind of recall at the beginning, you do observe brown PPT first. Yeah, so for the first few drops. In fact, when you have added 1 cubic centimeters, you do observe brown PPT first. Maybe it's yellowish brown kind of like that kind of color, the PPT. And then it's only when you added more, then you start just to see the solution turns like kind of like a darker green, and then you start to see a dark blue mixture, etc. So yeah, so these are things which should be recorded down. So for example, things like this, which your classmate wrote, green. I mean, green. Not the best answer, but I think we can accept because the a mixture of brown and blue. Sometimes you can't really see it very carefully. Yeah. So I think the best answer will actually be brown and blue PPT, but I think we can accept green. Okay. But what is kind of missing here is that the mixture after adding everything. You should be observing a dark blue mixture, but it's not exactly missing. Okay, so he or she wrote blue PVD dissolve to give a dark blue solution, but this solution is still a mixture, so still uh, a mixture. Why is it still a mixture? Because it's not a clear solution. So there are some precipitates around, but you can't really observe the color. Okay, yeah. Then remember that whenever you perform filtration, you have to tell us the color of the filtrate, which was mentioned, so it's good. And then you also have to tell us the color of the residue, which was mentioned as well. Okay, and then after that, I think this is kind of moving on to this particular portion. So let me just box it up. Okay, so this part. To 2 cubic centimeters of the filtrate, you add dilute sulfuric acid. Yeah, so that is the part which I told you you have to add it very slowly and very carefully. And from there, you observe pale blue precipitate. So it's not exactly blue, it's pale blue. If you observe very carefully, it's between dark blue and white, so it's pale blue. And then that is formed, and then it dissolves in excess sulfuric acid to give you a light blue solution or pale blue solution. Yeah, so usually in chemistry, we'll describe it as pale blue, but you can write light blue as well. It doesn't really matter. Okay, yep. So that's it for 1B. I hope you from the lab demonstration, you do get to see some of the key observations and what to write. Okay, yeah. So we are going to move on to look at the experiment demonstration for 1C and D.
Okay, students, we'll move on to experiment C from practical 14. So this is the residue, which if you remember what we did earlier on, you can see that it is reddish brown. Of course, I think it's not so obvious from the camera, but yeah, it's actually reddish brown in color. So what we're going to do is we're going to follow the instructions. We're asked to put a filter funnel with the residue over a clean test tube, and then carefully add hydrochloric acid. So we'll just do that. So this is a clean test tube. Okay, so very carefully. Okay, so you can see some residual water here. So I think we'll just dry it. Okay, so I think at this point in time, you should know the identity of the reddish brown residue. It should be iron 3 hydroxide. Some of you in your practical, you thought that the unknown cation is iron 2 because you kind of like saw the green mixture becoming reddish brown, something like that. But this is not the case, because if it's a green PPT becoming brown and you get oxidized from iron 2 hydroxide to iron 3 hydroxide, it won't be so even. So you will see it as a rim of you see the brown patches at the rim of the green patches. So it won't be so evenly oxidized. Okay, so in this case, we can easily conclude that, or I mean, we can conclude that it's actually iron 3. Okay, for our unknown. Yeah. So what I'm going to do now is I'm just going to put a test tube. Okay, and I'm going to put it here, and then I'm going to use hydrochloric acids. Okay, so I'm just going to carefully add it at the sides. Okay, I need to be a bit careful here because I don't want to introduce copper 2 in unnecessarily. Okay, so you can see that okay, I'm just going to slowly add in. Okay, you can see it's quite clear over here. You can tilt a little bit more. Okay, so it's a yellow solution. You can check that out. Okay, and then it's very clear that in the filtering process, you are getting a yellow solution. So that is likely to be iron 3. Okay, so I'm just going to put it here. Okay, you don't need to wait for the reaction to complete, or rather, you don't need to wait for the filtration to complete, because if you read the instruction later on, right, they mentioned that you supposed to wait for the residue to completely dissolve, and then supposed to retain the solution for C part 2 and C part 3. So during exam, I think a good way of working through the problem is take a look at C part 2 and C part 3. From there, you will have a sense of the amounts which you need. So for C part 2, you're supposed to take 2 cubic centimeters and then put it in a boiling tube, and then put some zinc inside. And then for C part 2, just 1 cm depth, and then I'm going to add aqueous ammonium thiocyanate. Okay, so we probably will do C part 3 first because it's actually easier. Okay, so yeah, I can see that quite a bit of it dissolved, so I'm going to put a little bit more. Okay, so again, as I mentioned, you don't need to wait for everything to complete. So what I'm going to do is I'm going to change over. Okay. So I'm going to take another clean test tube. I think it should be clean. I'm just going to wash it a little bit. Okay. So we're just going to follow the instructions. Just going to take a little bit of the solution. Okay, from here. Okay, we're just going to swirl it. Okay. Okay, don't need to add too much. Okay, so I'm going to add ammonium thiocyanate. So let me find where is ammonium thiocyanate. Okay, so over here, I found it. It's ammonium thiocyanate. Okay, so please observe. Okay, do you notice this? Some of you describe this as a reddish brown PPT, but it's not a PPT, you know. It's actually a blood red coloration. Okay, so I'm just going to slowly point in from the side. You can see the blood red coloration. Can you see the thing? Okay, so maybe one way I can do is I'm just going to put a little bit of solution at the sides for you to take a look. I'm just going to put some more iron. Okay. Can you see that this thing turns blood red? I think it's quite obvious from the picture. Yeah. Okay, so blood red coloration. You don't need to add too much. Some of you add a lot, and then you don't know like what are you observing? Is it PPT or etc.? You don't need to add a lot. Okay. So I'm going to add a little bit more to probably to convince you that it's okay, blood red. Okay, so you can see that it's a very thick blood red coloration. Okay, so there's no PPT. Okay, so basically the solution stains the side. Okay, so this is a characteristic blood red coloration, and it's where thiocyanate actually displays one of the water ligand in iron 3, and this is the color you observe. Of course, the theory, the reasoning you're going to learn it under transition metal chemistry. So we're not going to go into details, but this is a characteristic test for iron 3. So just take note of it. Okay, the blood red coloration. So we're going to just let you check it out again. Okay, so it's a characteristic blood red. Okay, right. So I think we have enough solution. So now what we're going to do is we're going to put 2 cubic centimeters into a boiling tube. Okay, so I have a clean boiling tube over here. Okay, so just clean it earlier on. So I'm going to use a dropper. So I'm going to input 2 cubic centimeters. Okay. Okay, you can see that this is not really very yellow, so so it's probably contaminated with a little bit of copper too. Yeah, which sometimes you can't really run away from that. Okay, so but anyway, yeah, in this case, it's good enough for this purpose. Okay, so we're going to follow instructions. Okay, so I'm just going to shift it to the side because we are required to do some heating. So it's supposed to put in some zinc granules. And then after that, gently heat the mixture. And then after that, it's probably expecting some gases from there. Then we're going to test for it. Okay, so I'm just going to put in things which I don't need at the side. Get ready some zinc granules over here. Okay. Okay, I'm going to shift this here so that you can see the flame. Okay, so for C part 1, yeah, so this is the yellow solution which is obtained as the filtrate when we added hydrochloric acid to iron 3 hydroxide. Yeah, so I think the yellow filtrate does give you a very clear indication that it is indeed iron 3. Yeah, so the next step for C part 1, we're supposed to add some, or rather C part 2, I'm supposed to add some zinc granules. So this is the zinc granules. Okay, so I'm just going to just add some using the spatula. Okay, so just very carefully add some insights. Okay, so you can observe that at the very beginning, right, there is brief effervescence. Okay, just very brief. Okay, but you're asked to heat it. Okay, so I'm going to turn on the flame. Going to keep it for a while, just to activate. Okay, give it slightly more energy, so that the effervescence become more vigorous. You can see now it's a lot more vigorous. Okay, going to heat it a bit more. Okay, you can see that now the effervescence is very vigorous. Okay, so what I'm going to do now is I'm going to test it. Okay, so actually I can hold it at the top of the boiling tube because it's not so hot. Yes. Okay, you can see that the effervescence is very good. Okay, I'm going to test it with a burning split. So I should be collecting the hydrogen. Okay. So can you hear the sound? Okay, so let's try again. Okay. Okay. Right. So I'm going to switch it off. I'm going to slow it. Okay. And then after that, we're going to check out this particular solution. Okay. Right. Okay, we are done with C3. Okay, I'm going to shift this away because it's a bit dangerous to have it here. I'm going to shift this away. Okay. I'm going to reposition my things a little bit. Okay, so just pardon me for the delay. Reposition this a little bit. Okay, right. Okay, so okay, back to this. Okay, so just hang on for a little while. My apologies. Just going to put things in a good order. Okay, then what we're going to do now is we are supposed to add 1 cm depth of Fa1 in a test tube, and then add 1 cm depth of aqueous potassium iodide. Okay, so I'm going to take another test tube. So again, a clean test tube. Okay, 1 cm depth of Fa1 in case you forget how Fa1 looks like. Okay, so Fa1. So 1 cm depth. Okay, so just nice. Okay, so now I'm going to add potassium iodide. So where's potassium iodide? It's brown bottle. Okay. Because iodide is sensitive. Okay. So please observe, because many students can't get this right. Okay. Now please observe what. Okay, I'm going to add 1 drop first. Okay, just 1 drop. Okay, what do you notice after adding 1 drop? You see a bit of solution turns a bit yellow, right? I don't know whether you observed that. Okay, turns a bit yellow. So I'm going to add 1 more drop. Okay. Can you see some bit of PPT forming, especially at the side of the corner? Okay, so I'm going to teach you a technique. You can turn, you tilt the test tube a little bit. Okay. Okay, so that the side of the test tube, the wall of the test tube, okay, will be filled with a little bit of the solution. Okay, then add it in again. Okay, add this in. Again, at the side, from the side. Can you see the side? Can you see the wall of the thing? It's a bit of white precipitate, right? Can you see that? Yeah. Okay, so there's another way you can do that. Take some more Fa1. Okay, I just drip 1 drop at the side. Okay. You let it flow in. Okay. You can see that the 1 drop is here, right? Okay. So I'm going to add this to the same 1 drop. Slowly up. Can you see? Can you see the trail left here? It's a bit of white, powdery PPT, and then there's a bit of brownish solution. Yeah, can you see that? Okay. So if you follow the instructions, I mean, you should follow instructions, but if you just do it the way you normally do it, right, then you don't get to see, you don't really observe all these nitty-gritties, right? Then you're going to write whatever you will write in your observation. Okay, Ken? So now we have a sense that, okay, I mean, when I add iodide, then I get brown solution forming, and then I get a little bit of white PVT. Yeah, then you can add more, right? So that, okay, so I'm going to add more now. Because I'm supposed to add 1 cm depth, right? So I am just going to just follow instruction add. Okay. Now, most of the students, right, they will just add, and then this is what they observe. Then they will write brown PPT. But the PPT is actually not brown. Yeah, the PPT is actually white. And the brown is actually the solution due to the production of iodine. How do I know it's iodine? Well, later on, the next step is also add thiosulfate. So when you add thiosulfate, a lot of students wrote in the wrong conclusion, like the brown PPT decolorized to give you white PPT. This is not possible. Well, I mean, it could happen to some compounds. Okay, and then if you want to observe, I think a very good telltale sign is to get the side of the container. I mean of the test tube. Just now I was telling you, okay, the side of the test tube. So maybe I can use this. We can. It's a clearer look. The side. Okay, so it's like a bit white. So yeah, because copper 1 iodide as a PPT, right? It likes to stain the walls of the container, especially test tubes. Okay, yeah. So if you wish, okay, a little bit more. Okay, okay. So now it's very obvious, already. Can you see the? Okay, so white powdery thing at the side. Yes. Okay, so if you leave it long enough, you'll see some of the white PPT settling down. Okay, but sometimes we want to, you can see it at the side as well. Okay, but sometimes we don't want to leave it for so long because we need to rush through the lab, right? Yeah, so I think a little bit of experience does help. Okay, so what I'm going to do now is I'm going to add thiosulfate. So this thiosulfate. Okay, so I'm going to just add it in. Then this is what you're going to observe. Okay, I'm going to add and swirl. Can you see that the brown solution actually lightens up a little bit? And then the white PPT become more and more visible. Okay. Okay. Can you see that? Okay. Yep. So I'm going to slowly add. Okay. It's a bit like a milkshake kind of thing, but yeah. If you don't add enough, this is what you observe. Yeah, that's the problem with sometimes, you know, when you are doing the practicals, you don't exactly know what's going on. Yeah. So if you add enough, then let me just show you. You'll see the brown solution actually decolorized. Yeah, because the iodine is now gets reduced to iodide. Okay, so you're going to get this brown solution. You're going to use a towel to clean a little bit. Yep, so this is what you should be observing. If you add a little bit more, yeah, remember the swirling technique? Okay, so this is the white solution. No, sorry, not white solution, the white PPT. Okay. Yep. Okay, so this is what you should be observing. Some of you notice that the white PPT actually dissolved in excess thiosulfate. You're not wrong, you're right. Okay, so we can try. Okay, I'm going to take a little bit of this. Pour it in. Okay, just a little bit of the white PPT. I'm going to add excess thiosulfate. Okay, the reason why it happens in this particular manner is because the white PPT is actually copper 1 iodide. So copper 1 actually forms a complex with thiosulfate. Okay, so please check. You can see the solution actually clears up. Okay, so I have a glass drop. Okay, yep. So the copper 1 iodide actually dissolved in excess thiosulfate to give you a colorless solution. Yeah, because of the formation of the copper 1 complex. Okay, quite a number of you observe it. Some of you didn't observe it, is fine because it's not a requirement to get the credit here. Okay, so just compare the two. So this is the one with the copper 1 iodide. This is the one with the complex. Both contains thiosulfate. In excess, limited. Okay, right. Now let us check out. Okay, our C part 2. What do you notice? Okay, a lot of students didn't do until here. Okay, straight away you just write a conclusion. Do you notice this very clear cut? Okay. What do you notice? The yellow solution actually decolorized. or you can say it fades to a lighter yellow. So it depends on how much zinc you have added. So yeah, the yellow solution decolors. Why is that the case? Some of you might be wondering, why is that the case? The reason for this particular decolorization, right, is because iron 3 is reduced to iron 2, right? So iron 2 is probably pale green, and you can't really observe the pale green that well due to its concentration. And then you are asked to decant the cooled solution into a second test tube. Okay, so I'm going to take a second test tube here. Okay, I'm going to pour it in. Okay, so decant. So just very carefully pour some of the solution in. Okay, and then I'm going to add aqueous sodium hydroxide dropwise until no further change. Okay, so this is sodium hydroxide. Okay, I'm going to add it dropwise. Okay, so please observe. Do you notice the formation of the gelatinous, dirty green precipitates? Okay, it's quite gelatinous here. Okay, I'm going to add more so that, because until no further change. Some of you will be wondering, how come there's white PPT as well? Okay, so the white PPT obviously is due to zinc. Okay, so because zinc in the reaction, right, it also reacts with hydrochloric acid to give you zinc 2. And then in the process of reducing iron 3 to iron 2, it also gets oxidized to zinc 2. Yeah, so the gelatinous white PPT and of course the green PPT is due to both zinc 2, and iron 2, sorry. Yeah, but because the question asks you to add sodium hydroxide dropwise until no further change, right? So you actually, I mean, in your observation, you can write a mixture of white and dirty green PPT observed, but when you add excess, actually only the dirty green PPT remains, as seen from here. Okay, so I'm just going to stir it a little bit. Okay, so this is what you observe. So this is the dirty green PPT for C part 2. All right.
Okay, yep. We are done with 1C and D, and now I'm going to review it over here. So if you recall, for 1C, you do see that the residue is reddish brown in color. So that is a very clear indication that the residue contains iron 3 hydroxide. Yeah, so in that case, when you add hydrochloric acid, you expect the solution to be yellow in color, or even towards the darker yellow, or even brown, but it's more of yellow in color. Okay, yeah. So this is very clear cut. You need to write it down very clearly. What is the color of the solution which you observe? Okay, so many students actually didn't write it down. And you have to be very careful when you're performing this, or make sure that your hydrochloric acid does not touch any of the blue portion, because that might contaminate the solution and maybe give you a solution that is not exactly yellow, but more of yellow-green. Okay, so you have to be a bit careful. Yellow-green because contaminated with copper too. Okay, and then this particular portion, I think we did discuss in the lab demonstration. Okay, so when you add the two pieces of granulated zinc and then you warm it, the warming is really to accelerate the displacement reaction. Okay, so again, this can be done quite easily. Colorless, odorless gas, which extinguishes a lighted splint or a burning splint with a pop sound. Okay, so pop sound here. If you are wondering what exactly is happening, and if you are wondering how do we know whether we are supposed to test for hydrogen gas, right? Okay, so this is the part which I thought needs to be explained a little bit more lah. Okay, first of all, right, what you have in the filtrates, okay, or in the resultant solution. So there are two important ingredients inside. One is H+, which comes from hydrochloric acid, okay, And of course, another important ingredient which is responsible for color is iron 3 plus. Okay, so I'm sure you are aware lah. So the reaction between H plus and zinc, okay, is a displacement reaction, which you learned that in secondary school. So this particular reaction will produce hydrogen gas, and this is the hydrogen gas which you are testing over here. Okay, so you should already expect hydrogen gas because you are adding a relatively reactive metal into an acid. Yeah, so this is expected. Okay, but there is another role for zinc. Okay, so the other role for zinc is to reduce my iron 3 into uh, iron 2 plus. Okay, so plus iron 2 plus. Okay, so in that case, I will have 2 iron 3 plus and I will end up with 2 Fe2 plus. And this is also the reason why eventually, right, you're going to observe the solution to turn into pale green. Yeah, but if you recall what I've shown you earlier on in the lab demonstration, the solution actually turned colorless because the concentration of iron 2 is too low, so you can't really see or observe the pale green. Okay, so yellow solution turns pale green or colors. I think that's fine. Okay. Um, of course, this particular portion, iron 3 plus, will be reduced to iron 2 plus, and then zinc will be oxidized to zinc 2 plus. Okay, so yeah, actually this is correct. I think it's marked wrongly. So apologies to the students who I was taken a sample from. Okay, so this should be correct. Okay, so this is correct. And then after that, to another portion where I need to decant it out. If you recall, right, I'm adding sodium hydroxide dropwise. So this is the portion which you really need to be careful about because after the reduction, I'm only left with iron 2 plus. Yeah. So you have to be really, really careful about it. Make sure that when you obtain the solution, um, the reaction has more or less gone to completion. It shouldn't be a mixture of iron 2 and iron 3 when you test, because if you test this with a mixture of iron 2 and iron 3, you're going to get a very messy mixture. Okay, so yeah, so once you are clear about this, then you should be observing 30 green PPT. Okay, so 30 green PPT or just green PPT observed, insoluble in excess. Okay, insoluble in excess. Yeah, just take note of this. But for the dirty green PPT, right, if you leave it long enough, in the absence of zinc, of course, it will slowly be oxidized to iron 3 hydroxide. But it won't be oxidized in like 1 minute. Okay, it will be done maybe over a few hours. Okay, so most of the time, your exam will have been completed lah. Okay, and you also need to be a little bit careful about this because when you're adding sodium hydroxide, right, there is another cation which will be precipitated out. That is zinc 2 plus. Yeah, so you are very, very, very likely to observe white PPT of zinc hydroxide. Okay, but it doesn't really matter here because the instruction given to you is I added a no further change is observed. Yeah, so because of that, because zinc hydroxide is amphoteric, yeah, so you will observe that the solution will clear up, meaning that the white PPT of zinc hydroxide will dissolve to give you zincate complex. Okay, so the complex is ZnOH 4 2 minus. So this is a zincate complex which is colorless in color. Okay, yeah. So yeah, these are some of the little things which you need to take note of when you're writing your observation. Yeah. So when you're in doubt, please go back to the earlier video on the lab techniques so that you can observe them more clearly. Okay. Yeah. Then next we are moving to part 3. So we have 1 cm depth of the resultant solution. And then, yeah, so this is very clear cut. Yeah, so the correct description for the purpose of H2 chemistry is only blood red. Yeah, which I have shown you earlier on in the lab demonstration. Yeah, so blood red. Yeah, so if you are in doubt, please check page 5 for the description and for the types of complex form. Okay, the formula is given to you. Yeah, and as I mentioned in the lab demonstration, D is worst done of all, because most of the students don't really know what to write, and I have demonstrated to you the technique to observe um, a white PPT in brown solution. Okay, so I think that should be sufficient import. I mean, whatever I show you should be sufficient for you to be able to observe it the next time and to be able to write it out. So it's definitely not brown PPT. So if you observe it carefully, the PPT is either cream or white in color. Okay, so you should be cream PPT in brown solution. Okay, we do accept if you say a brown mixture. I think that's fine. But remember, if you tilt your test tube a little bit, you see that the PPT actually gets stuck onto the wall of the test tube. Okay, so definitely you don't observe blue PPT, so just be a bit careful. Yeah, so the cream PPT will be more obvious after you have added disulfate, because your disulfate undergoes a redox reaction with iodine, and in the process, it goes from ist. So two of these reacted with iodine, and then because iodine actually exists as a triiodide complex, so it's brown in color. So you give it a colorless I minus, okay, and then you're going to get S4O6 2 minus. Okay, going to get a sort of like a dimer. Yeah, and this is colorless as well. Then as I mentioned further, in the process, because you observe the cream PPT, this cream PPT, if you look it up, is actually copper 1 iodide. So this copper 1 iodide. Yeah. So this copper 1 iodide, right, will form a complex with thiosulfate. Yeah. So eventually, if you saw what I did earlier on, if I just take out a sum of the white PPT or the cream PPT, right, I added excess thiosulfate, it will dissolve to give me a colorless solution. Yeah. So a good when you are writing observation is to say whatever PPT dissolve in excess, in this case thiosulfate, to give me a colorless solution. Okay. In this case, if you're wondering what exactly is taking place, I mean, I can explain to you a little bit, but of course, page 5 explains to you as well. Yeah, so has a very interesting chemistry here, because in presence of iodide, um, it will be mildly reduced. Yeah, okay, so you'll be mildly reduced. Yeah, so technically, it will go through +1 and then 0. But in this case, what you're going to learn later on is um, based on standard reduction potential, but you don't learn it now, so under electrochem. Yeah, so it'll be reduced to copper 1, but copper 1 is not a very stable cation in the aqueous species. But copper 1 happened to form a colorless, I mean, not as a color, means a white uh, solid. Okay, a very, very insoluble precipitate with iodide. So this is the so-called the milky cream or white PPT which you observe. Yeah, so this is the cream PPT which you observe. Yeah, but of course, if copper 2 gets reduced to copper 1, then I would expect iodide to be oxidized. So iodide gets oxidized. Yeah, so essentially this is what happens. So um, copper 2 gets reduced to copper 1, and then iodide gets oxidized to iodine. So we have half I2 here and then 2I minus. Yeah, so if I balance this equation, this is how it looks like. Yeah, so the iron 2, sorry, not iron 2, the iodine it's the brown solution which you observed. That's why we have green PPT in brown solution. And this can be detected by, or rather, you can decolorize the iodine in the presence of thiosulfate. Yeah, so that makes it quite clear cut, because thiosulfate is usually being used to remove iodine in the solution. Yeah, and then you are left with copper 1 iodide. Yeah. So this is a characteristic reaction which you need to know for H2. So just ensure that you understand this particular reaction well. Okay. Um, of course, if you ask me, what are the other uh, cations which will be able to oxidize iodide? So another one is iron 3 plus. So we are aware that Fa1 from the front, um, Fa1 actually contains iron 3. Okay, so that means that are we also getting iron 3 oxidizing iodide to iodine? So my answer to you is yes. I do expect iron 3 uh, to oxidize iodide to iodine as well. Yeah, but that is not um, being discussed here. Why is that not being discussed here? It's not being discussed here because I think number one, we are not testing for the presence of iron 3 and iron 2 in the process, if you realize. Like for part D, I'm not asking you to test, hey, whether the solution contains iron 2. Yeah, so if you bring iron 3 and iron 2 into the discussion, I mean, I don't mean into the discussion here. I don't mean like into discussion here, but if you try to bring it in, then it gets a bit unnecessary and maybe complicated. Yeah, but for copper 2, it's important to bring it into discussion because you observe the copper 1 iodide as the creativity. Yeah, so that's the reason why in most cases the focus of the discussion is only on copper 2 to copper 1 and then iodide to iodine. Yeah, we don't mention iron 3 to iron 2. Although it happens as well. I mean, we're not saying it's not happening. Okay. Yeah. So we're going to move on to this part, which is part E. You're supposed to identify the two cations in Fa1. I think we have talked a lot. Okay. So right now is more on the answering technique. Uh, okay. So for the answering technique, quite a lot of the students don't answer this question very well. The reason is most of you fail to read the instructions given to you. Okay, so the instructions given to you is you are supposed to quote two observations as evidence. Okay, and very, very important, you are supposed to state the formula of any new substance form. Yeah, so many of you do not state the formula of the new substance form, and of course, you did not quote two observations. Okay, so first of all, I think we have to be very clear. Uh, how do we know that it is copper 2? Yeah, it is copper 2 from various sources. So, for example, okay, let me mention this particular portion first. When I say the white or the cream PPT. Yeah, so the reaction between copper 2 and iodide giving the cream precipitate is a characteristic reaction of copper 2. So it's kind of quite exclusive. Yeah, so you can quote that as one evidence and make sure you write out the formula as copper 1 iodide. Okay, and then the other parts which you can potentially explain is the filtrates, which is dark blue or deep blue in color. So this is characteristic of the formation of tetraamine copper 2 complex. Yeah, so this is the formation. So this is the dark blue. This is responsible for the dark blue solution. Yeah. So the tetraamine copper 2 complex is responsible for dark blue solution. And then when you added um, um, sulfuric acid, if you remember, slowly, you observe the formation of the pale blue precipitates. Right. So I think you can write that in as pale blue PPT, which is copper 2 hydroxide. Yeah. Okay. I think you should write it in. Because it's kind of like a way to recover the pale blue PPT. Not recover, but to showcase that indeed as a complex equilibrium being taken to this hydroxide tetraamine copper 2 complex and hexyl aqua copper 2 as a complex in the aqueous solution. Yeah, so these are the evidences which you can quote. Broadly, the two evidences. One is the dark blue solution, and then give the formula, and then pale blue PBT when you added the sulfuric acid dropwise. Okay, and of course the characteristic reaction involving copper 2 and iodide, giving the characteristic copper 1 iodide. Yeah. Okay, make sure you state the formula. The reason why a lot of you didn't get the tick is because you forgot to state the formula. Okay, then yes, your cat iron 2 is iron 3 and not iron 2, which I think I've mentioned many times in the review lab video, so I think you can refer to that. Okay, so what are the evidences? So many of you thought that the DDVT is a resultant of the formation of iron 2. That is not the case. Okay, yeah. So there are several evidences which you can quote for iron 2. Number one is over here. Yes, over here. Yeah. So the reaction or the formation of the blood red complex with thiocyanate. Okay. So I think you can quote this as one of the key evidences. So I can write it down here. So the formation of the blood red complex, which is the monothiocyanate pens aqua iron 3 complex. Okay, so this is the SCN and then H2O5. Yeah, 2 plus. Okay, so this is the formation of this complex when SCN minus is added to Fa1. Okay, so this is very important. And then if you notice earlier on, remember the very beginning here, the filtrate over here, oh sorry, not filtrate, the residue is brown. Then after I added hydrochloric acid, you get a yellow solution. Yeah, this is the portion, which is an indication that is iron 3 plus. Okay, so brown residue. Yeah, I think you need to mention this as well, because if you don't mention this, then you will not have enough evidences to support you. Okay, and then another key evidence is also over here when you added the zinc granules in, because when you added zinc granules, right, this particular reaction takes place, and then your final product is iron 2 plus. Yeah, so iron 3 gets reduced to iron 2 plus. Yeah, and that is why later on you observe over here the dirty green precipitate. Yeah, so it is important for you to recognize that in order for me to get iron 2 plus, I must start off with iron 3, because if not, what is the species which zinc helps to reduce? Yeah, so these are pretty important questions which you need to ask yourself before you write down your conclusion. Yeah, so just remember to read the instructions carefully. If they ask you to quote 2 observations, make sure you do that. If they ask you to state the formulae, so make sure you do that as well.
Alright students, please go and look at the review lab demonstration videos for part F before we come back here to review on what to write for the observations.
Okay, students, we'll move on to experiment F. Okay, but before that, let's take a look at what we did for C2. If you recall, for C2, we added hydrochloric acid to the reddish brown residue, and then the filtrate collected is actually yellow in color, so that contains iron 3 plus, and then we added zinc as a reducing agent, and then iron 3 was reduced to iron 2, and then we tested with sodium hydroxide, and then you can see that dirty green PBT was produced, and then for the filtrate, from the major batch of solution, I asked you to observe, and then the observation is supposed to be turn colorless, but it appears a little bit cloudy if you just rewind the video, you will notice that it's a little bit cloudy, right? So you might be wondering, how does it look like after you place it there for like an hour or two, right? So this is how it looks like. So can you see that it completely turns colorless? Okay, so yep. But of course, you can argue that well, I mean, iron 2 is supposed to be pale green, right? Yeah, but it is indeed iron 2 because if you just smell it, it has that blood smell. I mean, blood-like smell. Yeah, so yeah, iron 2 is inside. Okay, but of course, please don't smell in exams because you're not supposed to do that. Okay, but you know, sometimes our senses, especially smell, does play a very important role in identifying stuff. Okay, so now moving on to part F, right? So what we need to do is, I think the first thing we probably want to do is add 1 cm depth of FA1. So it's again FA1 here. Okay, test tubes. Okay, going to add in FA1 cm depth. So I think that should be sufficient. Okay, and then we're supposed to add silver nitrates. So this is silver nitrates. Okay, so silver is very sensitive to light. That's why it's in a black container. Okay, so I'm going to uncap it. So please take note of the observation. I'm going to put it a little bit closer so you can take note of it. Okay, can you observe a little bit of white PPT being produced? Okay, so okay, observe the wall of the test tube. It's coated with a little bit of the white PPT, right? Yeah. So if I continue swirling, okay, you can see some of the white PPT settling down below. Okay, and then of course some of it is being stuck at the side of the test tubes. You can observe. Okay, so I'm going to continue adding. Okay, and a little bit more. Okay, then you observe that most of the white PPT will have been produced. And then if I just hang on for a little while, you can see those at the side, and then below, those are the one which settles down. Okay, so I'm going to continue swirling. Okay, to ensure that they do get settled down, but they don't clump together. Because if they get clumped together, sometimes it's difficult to verify the test later. Okay, so if you read the instructions, allow any precipitate form to settle, decant the solution, and then wash the PPT with deionized water. Some students are not really clear about this step, so I thought I just want to demonstrate to you. Okay, so this particular step, what you need to do, so for decanting is basically carefully pouring the liquid away and then leaving the PPT behind. So when you pour away, right, you do not need to pour until, you know, like there is no PPT going into this empty test tube. Yeah, you keep some of it goes in, it's okay. So don't, don't be OCD about it. Okay, so just pour. Okay, I just do a very quick pouring. Okay, real quick. Okay, so if you are worried that there are still some solutions inside, so all you need to do is just to take a clean test tubes, okay, and then try to get rid of the solution. Okay, to the best of your ability. Yep. Okay, but you can see that the PPT inside, right, still contains bits and a little bit of the earlier liquid. So that's why you have this instruction: wash the PPT with deionized water. So I need to take the deionized water. So I need to wash it carefully, just one round. Okay, I just need to swirl. Okay, and then again, what you need to do is to decant this solution away. Very, very, very carefully. Okay. There are still some liquid, so it's okay. Just going to again use the dropper to remove the liquid. Okay, so that should be good enough. Okay, so this is the washed PPT. Okay, it need not be completely dry. I think this is fine. Okay, then moving on to the next part, add aqueous ammonia to the PPT. Okay, so and observed. Yeah, you have to do this particular step very carefully, because if not, your observation will not be accurate. Okay, so this is aqueous ammonia. I'm just going to add it in very, very carefully. Okay, you can see that the solution is colorless. So if you don't wash it properly, the solution will be a little bit colored. Okay, you can see that the PPT actually clumps together, right? So what you need to do is you need to take a glass rod and try to see if the PPT will dissolve. You can see that the PPT actually dissolves in excess aqueous ammonia. You can actually argue that the dissolution is not complete. Okay, so no problem. We can always add a little bit more. So we'll try to do that. Then we'll add a little bit more aqueous ammonia. Okay. So now you can see that the solution is completely colored. So your conclusion should be the white PPT dissolved in excess to give a colorless solution. Okay, so that's what you should be observing. Okay, so I hope that's clear enough. Okay, yeah, so the procedure. If I fast forward to part H, right, they actually ask, explain why the solution must be poured off before adding aqueous ammonia. Okay, so let's do a negative example. Let's say we don't pour off the solution. What's going to happen? Okay, so I'm just going to use a clean test tube and show you a negative example. I'm just going to repeat the same thing. Okay, but in this case, I'm just going to do it real fast. Okay, so again, silver nitrates. I'm just going to just add in everything because I expected you to know the observation because we just did it. Okay, so let's say I don't decant it away. Okay, because the question in part H actually asks, why must it pour off before adding aqueous ammonia? Let's say I don't decant it away. Okay, I want you to watch what will happen. Okay, can you still observe very carefully the white PPT dissolve? Okay, let's try. Okay, let's try. So this aqueous ammonia. Okay, let's try. Can you see? Can you observe that you actually get a lot of precipitate coming up? Are you able to visualize whether the white PPT dissolves? You can't, right? And then you'll be wondering what are all these, right? If you forget what are all these, please go back to part B. Yeah, remember aqueous ammonia ionized partially to give you OH minus. So earlier on, we kind of determined that the solution contains copper 2 and iron 3, right? So this is the complex mixture of the PPT, which you observe earlier on. Yeah, so if you don't decant it away, and even after you decant it, if you don't wash it with deionized water, this is the resultant, and you can't really give your full inputs of the observation. Of course, you can argue that, you see, the white PPT is below, I can observe. I mean, if you are sharp enough, of course you can. I mean, like, let's say I have a glass rod here. So if I stir, and then I observe that the PPT sort of dissolve in excess, and that's fine. But you also need to take note of one thing. There might not be enough molecular ammonia for you to complex with the silver plus. Okay, that means that in order to dissolve all the white PPT, I need to add excess amount of ammonia so that I have enough molecular ammonia to not only complex with copper 2 to form the tetraamine copper 2 complex, but also to form the diamine silver 1 complex. Okay, so we can, I mean, this is just theoretical, so let's see if it works that way. So we add a lot more ammonia. Okay, and then see if our theory works. Okay, so we put it in, and then you can see that you can observe that the PPT, more of it dissolves. Okay, but still, there are still some at the bottom. Yeah. So this is what we call very messy. You're going to get very messy results, and you can't really have a very good conclusion here. So That's the reason why we ask you to let the PPT settle down, to decant the solution away, to wash the PPT with deionized water, and then after that remove the water, and then after that you add aqueous ammonia, because then we'll be able to very clearly see if the white PPT can dissolve in aqueous ammonia or it can't dissolve. Yeah, so that's the way experiments are being conducted. Okay, so now for F part 2. Fa1 again, and then I'm supposed to add aqueous barium nitrate, and then add dilute nitric acid. Okay, so again, I'm going to add Fa1. Okay, then barium nitrate. So this barium nitrates. Okay, so barium nitrates over here. Okay, going to add dropwise. Okay, again, so please observe. Yeah, so you get a very characteristic PPT. So it's a little bit different from the one you observed earlier on. This is a lot finer. Okay, and I'm sure you should be aware that if I add barium 2+, actually what are you expecting? Probably sulfate, barium sulfates, or barium sulfite. Okay, and how do you know is it barium sulfate or sulfites? All we need to do is to test it with nitric acid. Yeah, which I'm going to explain to you later on when we are reviewing the practicals. Yeah, okay, so we get a white PPT, it's very fine. Okay, then I'm going to add nitric acid. So nitric acid is over here. Okay, so that's nitric acid. Okay, see if the PPT dissolves. Okay. Okay, the PPT actually doesn't dissolve. Okay, we can keep stirring. So the PPT, the white PPT remain insoluble in nitric acid. So this is a conclusive test to tell us that it's actually sulfates and not sulfite, or it's sulfate 6 and not sulfate 4. Okay, SO4 to max. Yeah, so that's it for the demonstration and showcasing to everyone how to perform the experiment. And then I think the rest of the review videos will be on how to actually go about attempting the questions.
Okay, I hope you find the lab video demonstration informative. So we will move on to look at what we should be writing for the observations. Okay, so if you recall what you observed earlier on, to 1 cm depth of Fa1, we added aqueous silver nitrate. So this is a test for anions. Yeah, so if you recall what is present in Fa1, there are 2 potential anions, so we don't know what they are. Yeah, so I think first of all, when you are adding silver nitrate, if you look at your QA notes as well as the second last page of your data booklet, you'll notice that you are probably testing for halides. So potentially it could be chlorides, bromides, or iodides. Okay, then in our case here, I think it's very clear cut because the appearance of the precipitate is a little bit different from that of aluminum hydroxide and even zinc hydroxide. It's not gelatinous, so it's a bit chalky. It's like chalk being chipped off, or those white paints being chipped off. So it's quite characteristic. So please remember this color, and it is very clear and very obvious that is white in color. Yeah. So but sometimes it's not so obvious. Sometimes it may appear a little bit cream, so you can't really differentiate between white and cream. And the reason why you need to add aqueous ammonia later on is really to differentiate between silver chloride and silver bromide. Yeah, because if you take a look at your QA notes, you notice that silver chloride dissolve in excess ammonia to give you a colorless solution, but silver bromide only partially dissolves. Yeah, so please ensure that you take note of the observation, because it's actually quite clear cut. Yeah, but of course, this particular experiment, there is a layer of complexity being added, because you do know that Fa1 also contains 2 cations, Fe3+, which we identified earlier on, and what's the other one? Let me try to recall. Copper 2+. Okay, copper 2+. So you have these two. And in the presence of aqueous ammonia, because aqueous ammonia ionized partially to give us OH minus, so you would expect iron 3 hydroxide and copper 2 hydroxide to precipitate out as well, which will cloud our observation. And indeed, this is the question being asked in the later parts. Okay, over here. Yeah, so over here for part H, I think I have already sort of answered it when I was doing the lab demonstration. Yeah, and I gave you a negative example as well, and from the negative example, you do take note that when we have aqueous ammonia being added without decanting the solution, the whole solution is actually quite messed up. It's a complex mixture of brown PPT, green PPT, and then after you get a dark blue complex, etc. So it's very difficult. Okay, as what your friend wrote here, very difficult to observe the dissolution of the silver chloride to give us the colorless solution. Okay, so because of that, then it is very important in our case here to perform the decanting. Okay, so you have to decant the solution, and then at the same time, if you don't decant properly, I think some of you didn't decant properly, right? Your observation here will be messed up because you're going to get some colored solution, and then you might get some precipitate coming out as well. So it's because you didn't decant properly and you did not wash the precipitate with deionized water. You did not observe the correct observation. Okay, so you just have to make sure that you follow instructions carefully, and most importantly, you need to understand the chemistry behind what you are doing. Okay, so in this case, why is it that when I'm adding aqueous ammonia, my halide will dissolve? In this case, my silver chloride will dissolve. Well, you do know that when we have silver chloride is able to maintain a small amount of Ag plus and a small amount of chloride by virtue of its Ksp. Yeah, but at the same time, we are also aware that aqueous ammonia will form a complex with silver. So silver plus 2 equivalent of molecular ammonia. In this case, it will give us a very stable complex known as diamine silver plus complex. So the formation of this complex will actually drive the position of equilibrium of 1 to the right, because it leads to the consumption of aqua Ag plus. Yeah, so because of that, silver chloride will dissolve, and what we are getting is a colorless solution because diamine silver plus complex is a colorless complex. Okay, so you should be observing white PPT dissolving in excess to give us a colorless solution. Okay, so next we are moving on to the test for the next anion. So in this case, we are adding barium nitrate. Okay, so those of you who remember what you did in secondary school, you will be aware that the addition of barium nitrate is to test for sulfates. Yeah, however, for A-level chemistry, barium nitrate can also be used to test for sulfites. So it's the difference between sulfates and sulfites. Okay, so you need to take note of the difference, and both of them are white in color. Okay, then in that case, how do we distinguish between the two? So we distinguish the two by adding dilute nitric acid to the mixture and see whether the PPT can dissolve or it remains as a white PPT. Okay, why is it that if it's sulfite it will dissolve? So we need to go back to our fundamental understanding. Okay, so first of all, we know that sulfite is the conjugate base of a weak acid known as hydrogen sulfite, and hydrogen sulfides, okay, is the conjugate base of another weak acid known as sulfurous acid. Now, do take note of the number below. Okay, so this is not sulfuric acid, it's actually sulfurous acid. So sulfuric acid is a strong acid, sulfurous acid is a weak acid. Okay, now what's going to happen here is that, let me just zoom in a little bit. Okay, so what's going to happen here is that well, if I have the white PPT of barium sulfide, okay, again by virtue of its KSP, is going to maintain a small amount. So this is the KSP expression, and then equilibrium 1, okay, it's going to maintain a small amount of barium 2 plus, okay, and sulfites in the system. Yeah, so the bulk of it is the precipitate. So the bulk of it is the barium sulfide white precipitate, but it's able to maintain a small amount of barium 2 plus and sulfide by virtue of its KSP. Now, what happens when we add nitric acid? So in this case, we are adding nitric acid. Okay, when we are adding nitric acid, right, we are providing a source of H plus. So the H plus will actually react with SO3 2 minus, and in the process it will give us H2SO3. Yeah, aqueous. So some of you are thinking, oh, should I write them out as two separate equilibrium? Means H plus SO3 2 minus to give us HSO3 minus, and then HSO3 minus plus H plus to give us H2SO3. Well, if you want to do that, you can, but I'm just shortening it in this case because it's perfectly fine to shorten it. Yeah, so in this case, we are actually forming H2SO3, and the formation of H2SO3 will consume SO3 2 minus from the first equilibrium. So in turn, it will cause the position of equilibrium of 1 to shift to the right. So when the position of equilibrium of 1 shifts to the right, it leads to the dissolution of barium sulfides. Okay, so this is what exactly is happening here. Yeah, so if you observe white PBT dissolve in excess nitric acid or in nitric acid, then that means that my unknown anion is likely to be sulfide. If it remains insoluble, then it's likely to be sulfates. Sorry. Okay, and whatever I've said earlier on, right, it needs to be demonstrated in part G, and quite a number of you, when you draft your answer to part G, it can be relatively sloppy. Yeah, so if you take a look at part G, right, you're supposed to identify two anions. So of course, chloride and sulfate, everybody can identify them, but you need to quote observations as evidence and justify your answer, and then again state formulae of any new substances formed. Yeah, so first of all, right, we need to state the formula of the new substances form, and I think I've demonstrated above already. So first of all, we need to identify the white PBT to be silver chlorides. Okay, so silver chloride is being formed and dissolved in excess ammonia to give the complex, which is the diamine silver plus complex. Okay, so we need to indicate this very clearly, the diamine silver plus complex. Yep. And then is there any justification that needs to be done? Actually no more, because we are only kind of like doing one experiment, so don't worry about it. And then for sulfate, what do we need to do? So most people will write white PBT, so it's very clear that the white PBT is BaSO4, which is insoluble in nitric acid, but I think it is important for you to justify a little bit more. So I think you have to explain that it can't be sulfites. Yeah, because if it's sulfites, it will dissolve in nitric acid to give us a colorless solution. And why does it dissolve? I think you have to probably make mention that, you know, sulfite is the conjugate base of hydrogen sulfide, and then hydrogen sulfide is the conjugate base of the weak acid H2SO3. Yeah, then I think it will be good. You may not want to write it down, but it will be good at the back of your mind to understand the chemistry behind why the barium sulfide were dissolved. Okay, so with that, I think we have come to the end of question 1. I think I have reviewed part H already, so I think we'll leave it. Yeah, but off the top of my head, I suddenly remembered that earlier on I did not address one little part, which I think my apologies. I need to go back all the way to the front because I realized that I talked about it too fast. Okay, I think I did not address why is it that in the presence of carbonates, and then when I add it into Fa1, which contains iron 3 plus, I think I mentioned iron 3 plus has high charge density, but I did not actually elaborate on why is it that CO2 will be evolved, and I didn't quite indicate to all of you the nature of the precipitate. Okay, so do take note of it. The precipitate, right, is not likely to be copper 2 hydroxide. Okay, sorry. The precipitate is not likely to be iron 3 carbonate. In fact, it is impossible that it is iron 3 carbonate. If you ask me, could it be copper 2 carbonate? So my answer to you is yes, it could be copper 2 carbonate. Yeah, it could be. So this green PPT is indeed a mixture of copper 2 carbonate and iron 3 hydroxide. What about copper 2 hydroxide? Well, it's a little unlikely, okay, but it is possible. So it's because carbonate do hydrolyze in water as well to give some OH minus. So it's actually a complex mixture. But right now, I think the discussion I want to move along is not exactly to debate whether is it copper carbonate or copper 2 hydroxide, because it could be both, or it could be one or the other depending on how much carbonate you have added. But I want to focus my discussion on what exactly is the identity of the iron 3 species. Could it be iron 3 carbonate? So my answer to you is no. Quite unlikely that it can be iron 3 carbonate. Okay, so I'm going to demonstrate it using I'm going to write out some equations here. Okay, so I'm going to find some space to write. Yeah, okay, so what exactly is happening is that first of all, right, iron 3 plus has 6 water ligand being attached to the iron 3 center. Okay, and being a cation with a high charge density, it will ionize partially to give us FeH2O5 2 plus as well as H plus. So the presence of a cation with high charge density will result in it undergoing hydrolysis or partial hydrolysis, if you want to be more specific. What are the other examples of cation with high charge density? So there are 2 others in H2 curriculum. So you have Al3 plus, aqueous, or of course if you want to be more specific, then hexa aqua aluminium 3 plus. Okay, and of course hexa aqua chromium 3 plus. Okay, so these 2 have high charge density together with iron 3. Are they the only one? No, there are many others, but we don't really want to consider all for our curriculum at this stage. So as long as you know that they have high charge density, so the solution is likely to be acidic. Okay, then if it's acidic, one thing that is likely to take place would be the acid base neutralization between carbonates and H plus. Yeah, because in the presence of H plus, carbonate will react with the H plus readily to give us CO2 and H2O. Yeah, and this evolution of CO2 is what we observe as effervescence, and in the process it will push the position of equilibrium of 1 to the right. So POE of 1 shifts right. Okay, and it really depends on how much H plus I have, because if the concentration is too low, this whole process will take a relatively long time, and because it takes a relatively long time, some of the CO2 might escape, and there might not be enough CO2, and that's why it's very difficult to observe your lime water or white PPT in the lime water. Yeah, so that is the reason. Okay, and if let's say I have a relatively concentrated solution of iron 3 plus, yeah, then I would observe relatively vigorous effervescence. Okay, so giving us this particular species, but that is not all, because the reaction will actually continue to generate more H plus. So we're going to have a third and fourth equilibrium taking place. So for the third equilibrium, the iron okay, sorry, I think I missed out the OH here. So there's a OH. Okay. Then the FeH2O5 OH. Okay, this again will partially ionize to give me FeH2O4 and then OH2, and this is also aqueous, plus H plus aqueous. Okay, and then finally, of course, if we really add in enough carbonates, the position of equilibrium of 3 will be pushed to the right, and then the unipositively charged ion species will continue to undergo hydrolysis. Okay, and then it will lead to the formation of this neutral species, what we know as iron 3 hydroxide. Okay, so this is kind of neutral. Okay, so it will not be able to form favorable interaction, ion dipole interaction with water, so it will precipitate out. So this is likely to be the precipitate we observe. Yeah, but there are a lot of factors which really affect eventually what species we will get at the end of the day, because it's concentration dependent. So it could be a mix of these species, but of course the PPT you observe, if you, I mean, all situation being ideal, right, you would observe the reddish brown precipitate of iron 3 hydroxide with the 3 water ligand as well. Okay, yeah, so with this, I hope you have a better appreciation of the chemistry of the production of CO2 from a cation ion with high charge density, which I didn't explain earlier on. Yeah, I spent a lot of time trying to explain part B, but didn't really spend time talking about parts A. Okay, so moving on, next we'll be discussing planning. Okay, and after planning, that will be the end of the review for this particular practical. For the planning, we are given 4 cations. So you were told that this particular mixture contains the 4 cations, Al3+, copper 2+, iron 3+, and barium 2+. And out of the 4 cations given to you, 2 of them are quite familiar to you because we have dealt with them in this particular practical that is in question 1. Yep, so you should be quite familiar with the chemistry for copper 2 and iron 3 and what kind of color you are expecting. Yep, and of course for aluminum 3+, if you look at your QA notes, you are probably aware that Al3+ will form a white PPT with sodium hydroxide and as well as aqueous ammonia. So the white PPT is actually aluminum hydroxide. Yeah, but aluminum hydroxide is amphoteric, so it will react with hydroxide further to give you the aluminate complex. Yeah, so that is something which you probably want to take note of, because we could be using sodium hydroxide as one of the reagents to help us distinguish between all the 4. Okay, and of course you know the role of barium 2+, because barium 2+ don't give you any precipitates with sodium hydroxide or even aqueous ammonia. Yeah, but sulfuric acid will give you a white PPT of insoluble barium sulfate. Yeah, so that's probably one of the key reagents you might want to leverage in. Okay, but before we move on, we need to look at the instructions very clearly. We are supposed to devise a sequence of steps by which each of the anions in a given solution could be separately precipitated. So that means that our unknown cations, right, must be precipitated out individually. Yeah, so even if it's present as the complex ions in the filtrate, it's also not allowed. Okay, so they must be precipitated out individually. Yeah, so that's something you need to take note of. And then you were told that your plan should include expected observation and location for the ions. You may present your answer in the form of a table or flow chart. Okay, so in that case, you probably want to include the reagents in, so you can actually follow some of the way the tests are being written from the test in parts A to parts F. Okay, so from the way they are written, I think you are able to think about what is the best way to devise the steps. But of course, this is not the only way. Yeah. But I mean, at the same time, I think the thought process is very important. So the thought process in coming up with the flow charts is probably more important at this stage. Yeah. So with that in mind, let us try to draft something from here. Okay. So the first thing I think you manage to sort of realize is that Ba2 plus can be precipitated out individually. Yeah. So one of the ways to actually separate them is you separate them one by one. So you get Ba2 plus out, and then maybe you get Al3 plus, and then maybe copper 2 plus, and iron 3 plus. Yeah. Another way is you separate them in twos, in a pair. Then after that, within each pair, then you separate them further. Yeah. So that might be a little bit more efficient. Yeah, but again, there's no right or wrong answer. So we'll try to see whether we can perform the separation in pairs first. Yeah, so because if we can do that, then I think that is probably something we wish to follow. Yeah. Okay. So the first reagents which I think we can straight away think of will be sodium hydroxide. Yeah. Because when we introduce sodium hydroxide to the mixture, right, we have a mixture of Al3 plus, Fe3 plus, Cu2 plus, and Ba2 plus. I think the first thing we can do is to add sodium hydroxide to the mixture, because if we add sodium hydroxide, especially in excess to the mixture, right, Al3 plus will form the aluminate complex. Ba2 plus will not form any PPT, whereas copper 2 and iron 3 plus, each of them will be precipitated out as iron 3 and copper 2 hydroxide. Yeah, so maybe the first thing we might want to do is to introduce excess OH minus. Yeah, so if we introduce excess OH minus, iron 3 plus will be precipitated out as iron 3 hydroxide, and then copper 2 plus as copper 2 hydroxide. Okay, and then we'll perform a filtration, and then after the filtration, we are going to get Ba2 plus and AlOH4 minus in the filtrates. Yeah, so these two will be in the filtrates. Okay, and because they are in the filtrate, which is alkaline in nature, yeah, I think the first thing we need to do, right, since they are alkaline in nature, is to add, I think first thing is excess sulfuric acid. Yeah, so from here we can add excess sulfuric acids. Yeah, because once we added excess sulfuric acid, right, barium 2 plus will be precipitated out as barium sulfate. Okay, so in that case, barium sulfate will be separated. Okay, Al3 plus or aluminate will react with the excess acid, and in the process, we'll get back Al3 plus aqueous, or you can write it as hexa aqua aluminum 3 complex. Yeah, then with that, the Al3 plus can be precipitated out as aluminum 3 hydroxide using aqueous ammonia. So from here, I'm going to add aqueous ammonia, and then Al3 plus will be precipitated out as white aluminum hydroxide. Okay, so this will be precipitated out, and that's it. So we separate two from here. Okay, and then what about the residue? Okay, so for the residue here, we need to do something about them. So for the residue here, right, again, we can't work with solids. Yeah, so the first thing you might want to do from here, right, is again add sulfuric acids. Okay, maybe sulfuric acid is a good choice, H2SO4, to acidify a solution. Yeah, because after you have added sulfuric acid, right, what you are getting is a mixture of iron 3+, or hexa iron 3+, and copper 2+. Okay, and these two can be easily separated based on what we have learned above. Okay, how do we do that? We will add excess ammonia, excess aqueous ammonia, and then once we added excess aqueous ammonia, the filtrates, okay, so we have filtrates. The filtrates will be the complex, which is the tetraamine copper 2 complex. Okay, and then the residue. So the residue will be iron 3 hydroxide, which is fine, which is what we wanted. So we have obtained iron 3 hydroxide as the residue, which exists as a precipitate. Okay, then what about this? We can't just obtain this as the filtrate. So again, we need to repeat the whole process. So we need to introduce sulfuric acid to get back copper 2+, or hexa aqua copper 2, and then after that we need to introduce sodium hydroxide. Okay, so once we introduce sodium hydroxide, we will get copper 2 hydroxide as the precipitate. Yeah, so from here we'll be able to get the precipitate out, and then we are happy with this. Yeah, so we have successfully separated all the 4 as the precipitate. Okay, so 1 here, 2, and 3, and 4. Okay, so this is the broad thought process which you might want to look at in performing such planning. Of course, all road leads to Rome. You don't really need to separate them in pairs, and then after that within each pair you separate them out. Okay, so what I'm going to show you is one of the example done by one of the sample done by your classmates, and then we'll take a look at how we can benefit from this. Okay, so for this particular sample, right, yeah, what your classmate did was, I think first of all, excess sulfuric acid was added, and then you get white PBT or barium sulfate being separated out. Yeah, so out of the 4 cations, so I'm just going to list them down, so it's easier for us to follow. Copper 2, iron 3+, iron 3, aluminium 3+, and after that the final one is Ba2+. Okay, so so what happened was Ba2+ was separated. Okay, and then after that your classmate actually described the solution, probably took inspiration from what we had earlier on. Yeah, so it's a green solution, it's correct. And then after that the precipitate was being washed, so that's fine. And then after that to the filtrate, sodium hydroxide was being added until in excess. So in that case, you expect copper 2 and iron 3 to be precipitated out as copper 2 hydroxide and iron 3 hydroxide, and then yeah, so you get a mixture. So it's being described as brown. I think that's fine, but it should be probably more of like a greenish in color as well, what you observed earlier on, but I think that's fine. I think for planning, we try to cut a little bit of slack, but I think what is important is it will be quintessential to maybe share with the examiner what is the nature of the PPT. So in this case, we are really looking at iron 3 hydroxide and copper 2 hydroxide. Okay, yeah, but what is even more important is this particular step. Filter, and then I get a residue. Okay, so that's fine. Filtrate is colorless. Yeah, so this is the step which I often get while I look through the sample of planning given by all of you lah. So probably took inspiration from practical 15, or maybe even the question involving the slow addition of sulfuric acid to tetraamine copper 2 complex, where you observe a brief appearance of the PPT of copper 2 hydroxide. So because of that, the students maybe took inspiration from that and then wrote this. You add sulfuric acid carefully, and then you get the white PPT. But your white PPT is what you are getting is aluminum aluminum hydroxide, which is definitely soluble in excess acid. So you have to be a bit careful here. Even if you are very careful and you try to filter, right, you can actually try it in a real practical situation. You don't get much PPT because that particular precipitate which you observe, right, it's actually in a very awkward position because it's in a system where it's not very alkaline, not very acidic. So it's trying to find its balance in this very complex mixture, equilibrium mixture of stuff. Yeah, so that's definitely not the best way to perform filtration on the precipitate. Yeah, so as I mentioned earlier on, probably the best way is, in this case, is to, in the filtrate, you add excess acid and you turn everything into Al3+, and then you add aqueous ammonia to the Al3+ to get copious amounts of aluminum 3 hydroxide as the white PPT, and then you perform a filtration. Yeah, so that might be a much better way of obtaining the precipitate. Yeah, so this is a food for thought. So I hope you understand where I'm coming from. Okay, and then I think the rest are minor details, because what we have here is really what we have already experienced. But maybe another thing I thought I just want to share with all of you is that okay, so in this case the acid was added to dissolve the copper 2 hydroxides and iron 3 hydroxide, and then I get back the green solution, and then I added excess ammonia. Okay, so everything else is okay, so everything else is correct, so no issue with this. Yeah, but what some students asked me before was, is it actually okay to add aqueous ammonia directly into these two hydroxide, hoping that as I said, hoping that copper 2 hydroxide will dissolve. I mean, that is a possible steps. I'm not like saying no but it might not be very efficient, because sometimes when you are doing it, you might not be able to get a lot of the copper 2 hydroxide dissolved at the same time. I mean, it is possible. Theoretically, yeah, but sometimes practically when you carry out, it's not as easy as it seems yeah, so it's always better to actually convert all of them back into the aqueous ion form before you form the complex. Yes, so I hope you find this particular review of practical 14 important and useful for your learning. And do note that this is one of the many QA which you're going to do, and because this is the first QA, so I thought I should spend a little bit of time in developing some of these resources, especially the lab demonstration, to help you remember the observation which you should be getting. Okay, so with that then I'll see you in the next video. Thank you very much.